So the last video for this sequence is for the haloalkanes is the reaction of aqueous silver nitrate in ethanol. Now there are two important things. The first thing is this is an example of a this is actually an example of a nucleophilic substitution reaction. Substitution. Why? Because they are saying water is acting as a nucleophile over here. So this is a nucleophilic substitution reaction. It can also be considered as a hydrolysis because you are talking about aqueous. So because of this aqueous, you can also consider this as a hydrolysis reaction, breaking with the help of water and so on. Another important thing is you are using a silver nitrate. So silver nitrate is used to identify the halide ions. So if you use all this information, I would say that I'm using this to test for haloalkanes. So it is basically this reaction is being used to test for the haloalkanes. Now when I say test for haloalkanes, haloalkane means Rx. So I want to identify this part. I want to identify what is the X, whether it is the chloride or the bromide or the iodide, using aqueous silver nitrate solution. Now the good thing about this reaction is that what are you going to record? You will perform the experiment in a same way, but what are you going to record? That helps us to get three different results or information based on what are you recording. Like for example, if you are recording the color of precipitate, if you are recording the color of precipitate, then this will help us in identification of halide ion based on the color of the precipitate. Other thing is if you're recording the time, recording the time for the precipitate to appear for both of them, then you can get two informations depending on the type of substance you are using or the type of haloalkane you are using. You can get two different information by recording the time for the precipitate to appear, but that will depend on the type of haloalkane or what is our intention or objective. One thing you can get is, one information which you can get is, you can figure out the relative reactivities of primary, secondary, and tertiary haloalkane. Based on this, you can find out whether your haloalkane is a primary, secondary, or tertiary, or you can say you can compare which of them is more reactive, the primary, secondary, or tertiary. That is one thing. The other thing is you can also figure out the relative reactivities of chloride, bromide, and iodide. That means everything remaining constant, same, the alkyl part. If the chloride, bromide, and iodide is the only difference between the haloalkane, then how is the reactivity different? The way to do the test is same, but the information which you will get, that will help us to determine whether you want the identification, whether you want the relative reactivity of the primary, secondary, tertiary, or you want the relative reactivities of the chloride and bromide. As I told you, the way to carry out this reaction is exactly the same for all the three things. So one important thing before we move further, we should remember that with aqueous or with water, actually, you are adding aqueous silver nitrate. Now, when you are adding an aqueous, that means there is a water. Remember, water plus haloalkanes, they form alcohol. So there is a possibility of a question being asked, like you are adding silver nitrate, water, and to this alcohol, to this haloalkane, what will be the organic product? So this is your organic product form. This is your organic product form. For example, if I am taking, let us say, CH3, CH2, Br, and I'm reacting it with HOH, I'm writing it just for the sake of understanding. What will happen is this HBr may combine to form the HBr, plus you will get the alcohol, plus OH, you will get the alcohol. So you are starting with, this has been already explained in the previous video, you are starting with bromoethane, you will end up with ethanol. You will end up with ethanol. So depending on how many carbon atoms are there, that will decide the alcohol. Whether you take a chloroethane or the iodoethane, that does not matter. What matters is this thing. Alcohol is formed. So what matters is the number of carbon atoms. If there were 3 carbon atoms, you will get a propanol. If there were 4 carbon atoms, you will get a butanol. That will be the organic thing. The other thing is this is a HBr, which is acidic. So since it is acidic, it will break into H plus and Br minus ions. This Br minus ion is what you are going to identify with the use of silver nitrate. Now remember again one thing, that haloalkanes are not very soluble in water. So for that we have some extra measures to take. So this could be Br, this could be Cl, this could be I. So depending on the color of the precipitates, you can identify. So you are getting the halide ion from here. Because of this reaction with water, hydrogen halide is formed. That hydrogen halide is being used by AgNO3 for giving you the precipitate. So keeping all this thing in mind, now let's focus on what is the procedure for the test. Now there are many times there are additional questions for this, so we will talk about that. Now what we do is, for this reaction to take place, you will take a haloalkane, you will take some NaOH, you will add few drops means small amount. Basically I'm writing a few, it means a small amount. Sometimes they may say 1 cubic centimeter, 2 cubic centimeter, 3. So that means a small amount of ethanol, and then some amount of water. Now then if you look over here, what are you doing over here is that, remember, with water, pure water, hydrolysis is slow. So that is why you are using in a basic medium. So NaOH is just making it basic. That's the first thing. Now there are questions. So this way, this combination provides a basic hydrolysis. And why are you doing this? To increase the rate of reaction, to increase the speed of the reaction. Otherwise it will take longer time. That's the first thing. The second thing is why the ethanol is being added. Why the ethanol is being added. So you only need to say that this is behaving as a co-solvent, or you can just say a solvent. Why I'm using the word co? The reason is water is already there as a solvent. So this is in addition to water, this is also behaving as a co-solvent. Co-solvent, why? Because remember, haloalkanes are not highly soluble in water. Haloalkanes are not highly soluble in water. So when you are doing this hydrolysis with NaOH and with ethanol, what are you doing is you are creating this condition, NaOH aqueous and NaOH alcoholic, both of them by adding alcohol. So in this combination, what will happen is both the silver nitrate and the haloalkane will dissolve. So if they ask you why ethanol is added, it is a co-solvent, it will ensure this is dissolved. All of it, AgNO3 as well as the haloalkane. So the actual thing is it is a co-solvent. So what co-solvent means that in addition to water, there is an alcohol also. So all polar, non-polar, any kind of substance. This is additional information where what is going to happen? Anything which is polar or non-polar, everything will dissolve. All polar and non-polar substances will dissolve. That is the basic aim of using ethanol over here, because haloalkanes are not very highly soluble in water. So when you are using an ethanol, it is providing an organic solvent for the haloalkane to dissolve. Now, why do you need the haloalkane to dissolve? Because when it will dissolve, it will separate out into its ion. The halide ion will be free, and then the halide ion can be tested. So I will write this again. What are you doing over here? Because there are too many things over here. So what you have done is you have taken your haloalkane. You have taken a haloalkane. You have added NaOH or KOH. You have added some amount of ethanol, and you have added water over here. So you know the importance of all of this. After this, you warm it a little and add dilute nitric acid. Now, this is sometimes in your exam, they may ask about this. Sometimes they don't ask about it. Dilute nitric acid. Now, why are you adding dilute nitric acid? Now, one of the important thing is we did this before, that it was to remove the carbonate impurities, but that was in inorganic chemistry where carbonate is one of the impurities most of the cases. But here, why are you adding it? Here, dilute nitric acid is added. This is to prevent any unreacted OH minus remaining. So what will happen is this OH minus being a base, it will react with the acid and get neutralized. Now the thing is, why you want to do this? Why you want to prevent any unreacted OH minus remaining? Because what can happen is this OH minus may react with silver ions coming from the silver nitrate and gets precipitated, gets as a uh, precipitate of silver hydroxide. So that will create an additional interference in your reaction. Silver precipitates will create additional interference in your reaction. So you don't want this to happen. So this is only for why you are adding a nitric acid. If and when a question is asked about this. Otherwise, you are adding all those things, you are warming. Now after warming, what you will do is the sequence needs to be followed. After that, you add silver nitrate solution. After that, you add a silver nitrate solution. Now what will happen? Now what are you observing? You are observing the colors. You are observing the colors. So based on the colors, you will decide what happens. So suppose you are recording the colors of the precipitate. So there is possibility of three types of precipitate, depending on the kind of haloalkane you have. If you have a white precipitate, which is dissolves, we talked about that before in the test for the halides, which dissolves in dilute ammonia solution. They can say dilute ammonia or they can say less amount of ammonia. So white precipitate that dissolves in dilute ammonia, you are 100% sure that the chloride is present in your haloalkane. And if you are getting a cream precipitate that dissolves in excess, or the word concentrated can be used, concentrated ammonia, then you are sure it is bromide. And you may get a yellow precipitate. This will be insoluble in concentrated ammonia. So with any amount of ammonia solution you are adding, it will remain insoluble. So your I minus is present. Bromide is present. So they may also ask you, what is this white precipitate? We have discussed that before. It would be AgCl, this will be AgBr, and this is your AgI. So this was also explained to you in a previous videos. So on the basis of this, once you know that it is chloride, bromide, or iodide, you know it is your either the chloroalkane or the bromoalkane or the iodoalkane. So you will be able to identify. This is one aspect where you were looking at or observing or recording the color of precipitate. So your aim was to identify. So you were comparing the colors. You were comparing the colors of the precipitate, and based on that, you were able to identify the halide. That's one aspect. Now, if I want to compare the reactivities of the chloro, bromo, iodo, then what I will do is to, if you want the relative, so this is the second type of experiment or recording of data, that is relative reactivities of, let us say, chloro, bromo, or iodoalkanes. You want to compare which of them is more reactivity. So over here, what you do is you record the time taken for the precipitate to appear. Now in this case, I'm not worried about the color of the precipitate. I'm worried about the time taken. That is one thing. The second thing is I want that since I want only the X group to affect the rate, not the alkyl part. So what we do is we take similar alkyl group. Like for example, I would, if I want, I would take a CH3CH2Cl. I will take CH3CH2Br. I will take CH3CH2I. So in this case, what happens is this part is common. This part is common. So their effect on the reaction rate would be same. The differentiating thing will be the chloride, bromide, or the iodide. That will decide the time difference for the precipitate to appear. In case of iodo, the precipitate appears quickly. How will the precipitate appears? NaOH, water, ethanol, warm, add dilute and nitric acid followed by AgNO3. The precipitate will appear. This will be instant. The moment you add silver nitrate, you will get the precipitate. This will take the precipitate takes longer to appear compared to. So remember, this is relative. You are not looking at exact timings, or you are just comparing which is more, which is less, nothing else. And this won't give any precipitate until you warm it a little. So under the normal circumstances, it will be the last to appear. It may take too much of time, or if you warm it, then you will get the precipitate. So what does that indicates? This indicates that the iodoalkanes are more reactive than bromoalkanes, because the iodoalkane, the precipitate appears quickly because this bond was breaking quickly, and the chloroalkane were the least reactive. We have already discussed that before. Why are they most reactive? Because the carbon iodine bond length, this bond length is maximum, while over here the CCl bond length among these halogens is the least. So if this is maximum, it breaks easily. Bond length is maximum means it breaks easily. So less energy will be required. Least energy will be required compared to this. So this is in conformation with what we have talked before, that the reactivity of the iodoalkane is more because the bond length is more, and by doing this experiment you are able to prove that the precipitate for the iodo appeared quickly. Now the third possibility is you wanted to compare the relative reactivities of primary, secondary, and tertiary haloalkane. Now, just like in the previous example or the test second one, we said we wanted only the X to affect the rate. So that is why the alkyl group was taken as a constant. Here, we want the structure to affect. We want the structure, that means the primary, secondary, and tertiary, to affect the rate. So what we will do is, if we want to do this test in the lab, we will take same molecule. So we will take over here for this experiment. If you want to perform this in the lab, for this experiment, you want to show that primary, secondary, tertiary, which is more reactive or less reactive, you will have to take isomers. Isomers means they should have the same number of carbon atoms and all, and the halogen definitely has to be the same. The halide ion has to be the same, Yeah. Why halide ion has to be the same? Because if in one compound, in primary you are having a chloro, in secondary you are having a bromo, and in tertiary you have the iodo, then in addition to the structure, the halogen ion or atom will also affect the reactivity. We don't want this to happen. We don't want this to happen. So if I'm taking in case of, I'm just giving an example. Let us say I had a tertiary bromide, bromoalkane. Then I could take there's 1, 2, 3, 4 carbon atoms. So this is your tertiary, this is your secondary, and so these all are isomers. They have the same halogen. So the halogen is not going to affect. The number of carbon atoms, the molecular mass are the same. So that is why we are saying they are isomers. So the only thing that is going to affect the reactivity is the primary, secondary, and the tertiary. And in, so what will be your observation? Now remember, what will you observe? You will observe record again, the time for the precipitate to appear. That is what we are going to record. In tertiary haloalkanes, the precipitate would be instant. The moment you add AgNO3, you will observe the precipitate. Secondary haloalkane, the precipitate appears after a while. And if you keep it, it becomes more, like there will be after a while. So if you initially there will be very less, some sort of slight precipitate. If you leave it for a longer time, more and more precipitates will appear. So it is taking time. It is taking time for the reaction to be complete. So that is why it is taking time for the precipitate to appear. And what is that precipitate? If you have taken a bromo over here, in all these cases, you are getting a cream precipitate. If you have taken an iodo over here, you will be getting the yellow precipitate. So the color of the precipitate will be the same, but it will be taking little longer than tertiary. And in the primary haloalkane, the precipitate takes much longer time. Maybe sometimes we may have to warm it also. So what does this gives us an idea? This gives us an idea that the tertiary is more reactive than secondary, and primary is the least reactive. Primary is the least reactive. So this is the order of reactivity. And this completes your topic for the haloalkane, the full topic for haloalkane. Now here you may be asked about the colors, you may be asked about the order of reactivity, you may be asked about what are the products being formed. Like I just told you, organic product is alcohol. Why are you adding NaOH? Why are you adding ethanol? What type of reaction is this? And so on. So you need to go through each one of them.